Victor Turchin from Kansas, Embeddings, operads, and graph complexes.
Thank you. I'm going to talk about some recent development in the study of embedding spaces. So my main collaborators are Thomas Willwacher, who talked today, Benoit Fresse. Also I worked with two young guys, Ducoulombier and Songhafouo Tsopméné. So let me start by kind of briefly explaining the idea of the Goodwillie-Weiss calculus. So first, so the idea really comes from the generalization of H principle. So what is H principle? So consider two smooth manifolds M and N, and consider the space of smooth immersions from M to N. So for this space, we can assign also the space of formal immersions. So the space of formal immersions is a space of monomorphisms of tangent bundles. So we want to have a morphism of tangent bundles compatible with some continuous map of the base spaces. So fiber-wise, it should be an injective linear map. So, and we have a natural evaluation map and the theorem of Smale-Hirsch from 60s, 70s says that this map is a weak homotopy equivalences provided the codimension is at least 1. So for codimension at least 1, where by codimension we actually mean the difference between the dimension of n and the handle dimension of m. So for my talk, codimension will always mean the dimension of n minus the handle dimension of m. So in particular, this weak equivalence holds for immersions of manifolds of the same dimension when M is an open manifold. So more generally, H principle is applied to the spaces of certain non-singular maps. So fix a singularity, which is some closed subspace in a space of jets, R jets, of Taylor expansions of smooth maps from Rm to Rn up to degree R. So we fix some closed subset which is invariant with respect to the action of the group of jets of diffeomorphisms, both on source and target. And for this guy, we can assign the space of smooth maps of one manifold of dimension M to another manifold of dimension N, which are non-S singular. So non-S singular maps. And there is natural map to the space of sections, so the similar relation map to the space of sections of over M of the bundle. So this bundle is so we take the space of jets. So we take it's really subspaces R jets from M to N. So let me denote it by S. So this is a space of S non-singular R jets from M to N. So it's the fiber bundle over M, and we just take the section space of sections of this fiber bundle. Right? Yes?
Can you just say a little more what you mean by this non-S singular map?
Right. So we fix a singularity. A singularity is a closed subspace in the space of jets. So space of jets is essentially the space of Taylor expansions of functions, so up to degree R. And so we fix a closed subset which is invariant with respect to the action of the group of the jets of diffeomorphisms of Rn and Rm, right, in around 0, right? And now we consider a space of maps which avoid this singularity, right? And it's actually a space of jets of maps, right? So this is actually a fiber bundle over n times n, right? But we look at the space of sections. So this is kind of this space of monomorphism is a particular example. So when we take R to be 1, right? So this is really a space of bundles. So for every point you assign a map, but really around. So for every point P, for every point X here, you assign a Taylor expansion of some map up to degree R, and it should be non-singular, non-S-singular, right? And so H principle tells you, so we have natural map, evaluation map, and the H principle tells is a conjecture, so sometimes it's true, sometimes it's not true, that this map is a homotopy equivalent. So it's really a question whether it's a homotopy equivalent or not. H principle. And the whole idea of this principle is that, on the left-hand side we have some kind of geometric problem from geometrical topology, right? We deal with smooth functions. So for example, it could be space of Morse functions, right? So we don't necessarily have this dimension of M is less than dimension of N. Or we can consider space of immersions, or we can consider spaces of, avoiding certain singularity. For example, we can allow birth-death singularity, right? But not allow high singularities. But on the right-hand side, we get essentially space of sections. It's like twisted mapping space, right? So so we really reduce the geometrical problem to homotopy theoretical problem, right? So it's a little bit like Thomas, who doesn't like topology. Me, I don't like geometry. I do the homotopy theory, right? So in case when we consider multi-singularity, right? So which should be viewed as a, roughly speaking, a subspace in the space of multi-jets. Multi-jets of a collection of Rn, right? So in the neighborhood of origins, and so we want to have some closed subset which is closed with respect to the action of group of diffeomorphism. And so now we can consider the space of maps which avoid this multi-singularity, right? So as example, we can consider spaces of embeddings. Well, also we can, I like spaces of non-k equal immersions. These are immersions which can have double, triple self-intersections, but they cannot have k-tuple self-intersections. So they are never constant on any subset of k points. Or one can also exclude, for example, maps having self-tangencies, right? So I mean, you can consider some kind of restriction on several points. And Goodwillie-Weiss calculus, it's really kind of similar machinery which replaces the geometrical problem to some homotopy theoretical problems, so which we call T infinity of this map. So let me call this also evaluation map. And also the question is whether this tower converges or not. And big result in the of the calculus, really for embedding calculus, criterion by Klein, Goodwillie, and Weiss. The last steps were actually completed very recently, like 2014, which states that for codimension at least 3. So again, by codimension, I mean the difference between ambient dimension and the handle dimension. One has that this map, so the map from embeddings to the limit of the tower is a weak equivalence. Just to kind of give you an idea of what exactly this map is. So, so what is this evaluation map? So we can consider the configuration of, right, so we can consider maps, sigma 2 equivariant map from the configuration of 2 points in M to the 2 points in N. Right? It's very natural, right? So when we have a embeddings instead of immersions is natural to look what we get when we consider this natural map, right? So we have this evaluation. But the thing is that it's not enough to consider just configurations with 2 points. We actually need to consider configurations of any cardinality. So we need to take the product going to infinity, and we need really to take here, maybe use different colors. Right, so this is your actual evaluation map. And again, you see that this space is far from being the space of embeddings, right? Because actually we need to impose certain conditions on the configuration. So for example, when points in configurations collide, right, we also want the image, in the image have the points colliding, right? Another restriction is that we actually need to consider frame configurations. Right? So and here we need to take partially framed configurations. Right? So when we have in your manifold a bunch of framed points, right, we want to assign, so they are sent by embeddings to, right, so when we have an embedding of M inside N, we get also the points in the image, right, and they're also going to be framed, because we can take the differential in these directions. Right, and well, the map is actually really invariant with respect to the framing as well. So as I said, it means that actually this T infinity is not really this subspace, but roughly speaking, is some subset here, right? So where we want to get some restrictions on the boundary, so how points collide, and also they should be compatible in the way when points are forgotten. And it turns out that the best way to describe what happens on the boundary is really to use the operatic approach. So operatic approach which Thomas was talking a little bit about, says the following. Theorem Boavida Weiss in 2015. So which says that actually the T infinity of this embedding space can be described as a space of right models, so in the derived sense, over the framed little disk operad. And so here we take the embeddings inter DM, and the target we take embeddings of a bunch of disks inside N, and this space of right models is really subspace of the product, right? So a similar subspace of the product of the sigma k equivariant maps from embeddings of k disks inside M. So I'm kind of sorry, I'm really running into the problem. K disk inside N. So, but the point is that actually the space which you have here is really frame configurations of k points in M, and this is frame configurations k points in M, right? And so we really recover the space, right? And also notice that there is natural evaluation map, right, from the embeddings. So given a configurations, a bunch of configuration of disk inside. No, I wrote something wrong. DM inside M. So given a bunch of disks, right? So this space is a kind of right. It's a really bunch of disks inside M, and so we can. So when we have like few disks inside M, the embedding assigns you by taking composition the corresponding configurations of disk inside N, and the same formula actually true for the space of non-singular maps. I should write it down. So T infinity for the space of S non-singular maps can be described in terms of right models of the framed disk operad. So here on the left we have this embeddings, a bunch of disks inside M, and as a target we have the S non-singular maps of a bunch of disks inside it. So you see that the target is no more the space of embeddings, right? But we really take the space of so and actually it's also a kind of product of spaces, but now instead of taking sections over the jet bundle, we have a sections of the multi-jet bundle, where at the base we have configuration space of k points in M, right? And so we have similar kind of space of sections. So this is kind of very fast introduction to the Goodwillie-Weiss calculus. And right, probably I should mention that the case approximation is obtained by saying that there are no more than k points in configuration. Right? So you go up to certain, from k equals to 1 to like degree n. Right? So if you have n's approximation. Good. So what happens when we deal with another theorem? So now consider the space of also S non-singular maps, but of the disks, right? And assume that M is less than or equal than N. And also we consider the maps which are relative to the boundary. So we assume that the map is the standard inclusion, equatorial inclusion of n-dimensional disk inside n-dimensional disk. And so we look at the space of S non-singular maps, like for example, space of embeddings or spaces of non-co-equal immersions, but again, which are standard near the boundary. So in this case, the limit of the tower can be expressed as a space of maps of infinitesimal bimodals over the little disk opera. So disks are flat, right? So you don't need framing. So that's why we don't have framing here. And the source becomes BM, and the target is following guy. So we get S non-singular maps from a collection of disks inside DN. So notice that
what does inf-bim mean?
right, it's infinitesimal bimodal. I'm going to explain in a second, right? So I'm going to explain what it means infinitesimal bimodal and what is the difference with bimodal. So that's really the way to take into account the boundary. So somehow your configurations of points can approach the boundary, right? Besides the fact that they can collide, right? They can also approach the boundary, and this is encoded by this algebraic structure, which is called infinitesimal bimodal. Actually, there are different terms in the literature. Some people call it abelian bimodals. Some people call it linear bimodals. So, and Markle, who first introduced this term, he just called it bimodals. Right? So let me explain what it is, this infinitesimal bimodals. So definition. So infinitesimal bimodal M over an operad O is the following object. So we want to have infinitesimal left action. So which are given by composition where we insert in one of the inputs of O an input of M, right? So this really the difference with the bimodal structure. In the bimodal structure, we insert in every input of O element of our bimodal. And infinitesimal right action, so we get, right, so we insert in one of the inputs, we have insertion of O. So this is really the difference, right? Just to compare with the bimodal structure, right? So what is the difference between infinitesimal bimodals versus actual bimodal?
Can you see what M is as an object?
Sorry, yeah, I'm very sorry, yeah. So they're symmetric sequences. they're symmetric sequences, right? It's true that I want to say that actually M is a collection of guys, right? Over operand, and operand is also symmetric sequence, and we are circle I, like we have a circle I operation which goes from O of k to M of L to mk plus L minus 1. So that's what really meant by this picture. Right.
Sorry to be insistent. Could you maybe also list some of the axioms of that satisfy? Or?
Probably not. I'm sorry, but I can tell you the category is the kind of that structure of an operand is encoded by roughly by the category of trees, rooted trees, right? And but here we want to take this kind of rooted trees with a marked point, right? Well, instead of listing the axioms, I'll just give an example, right? Okay, so bimodal. So the difference with bimodal is that we have the left action. So maybe I also give an example that in case we consider the associative operand, if O is associative operand, and we consider non-sigma case, non-sigma infinitesimal bimodal, then this structure is equivalent to the co-simplicial object, right, if this helps. So left action would be, in case of bimodal, is going to be given by inserting a bunch of elements inside O, right? And you see this is a difference. So bimodals, at least left models, they are more like algebras, right? We can multiply several elements using our operands, while the infinitesimal left action only uses only one element from your bimodal. So it's really kind of good. And so right action is given by the similar picture, but now you insert in every input an element of the operand. But because of the presence of the identity element in the operand, actually right action and infinitesimal right actions are equivalent. So there is no really difference. So the difference is in the infinitesimal left action and left action. And the thing is that when we take this collection so when we take this collection of S non-singular maps of disk inside the n-dimensional disk, right? So without any boundary restriction. So it's given by the collection of maps like this. So it's quite easy to see that this is actually both bimodal and infinitesimal bimodal. So it has both the structure of a bimodal over, so it is a BM bimodal and BM infinitesimal bimodal. Right. So, the fact that it's BM bimodal, it's actually easier to see that it is a BM bimodal. So it has left action by BN, so n-dimensional little disk operand by taking compositions with the target, and also it has right action of the m-dimensional disk operand. So that's why it has a. Then we just restrict left action on BM. So we have kind of these two structures, and so the natural question would be to compare, right? We have derived mapping space of infinitesimal bimodals, and now why not consider the derived mapping space of bimodal maps? Right, we can consider bimodal derived.
Sorry, that sentence. One of them should probably be an N, but I don't know which on that blackboard.
Say it again.
So one of those BMs, down, should be an N, but I don't know.
Both should be N.
Both should be N.
Now, both are BM, yeah. So the thing is that it's both. So what I mentioned is that why it is BM bimodal. it is actually more than BM bimodal. I say that it is a BM bimodal.
And is the smallest.
Right. So you have a right. So you have a on the target you have a like left action of BN and right action of BM. But what I want to take restriction as a BM bimodal, right? And it is also a BM infinitesimal bimodal, essentially because it is a bimodal and it has a map from BM. So the thing is that there is inclusion of this guy into this guy, and because of this, the bimodal becomes infinitesimal bimodal. The claim is that, so now if you look at the space of derived map of bimodals from BM to the same target, right. So no, I want to close make it so. The theorem is that actually what we get is a delooping. So we get M loop space here. So when we take into account this space, and so this is a result of Julien Ducoulombier and myself. And an interesting consequence is for the spaces of embeddings. So now let's consider just notation. So assume that M is submanifold in N. So we denote by M bar the homotopy fiber of the inclusion of the embeddings space into immersion. Right, so we take the base point to be this inclusion, right, and we take the homotopy fiber over this inclusion. So this is just notation. I want to always use it in the sequel. And the theorem says that if we consider codimension, no, in this case it's just n minus m. Right, so when the Goodwillie calculus is applicable, we get that the space of embeddings of dm side dn, and again we take this model immersion of the space of embeddings, it becomes m plus 1 loop space. So you can go one dimension further, and then you get the, instead of bimodal maps, you get the map of operads from BM to BM. Right. So the thing is that in case of the space of embedding model immersion, the right hand side becomes just the space. So the right hand side can be replaced by BN. So the whole thing, this becomes BN, right? And in that case, we can kind of go one dimension further. And this result was first proved by Boavida, Brito, and Weiss in 2015. Right, but so it also follows from our result. So it gives our result gives a different proof of this result. Also interesting what happens with a framed. So we can get a framed delooping of the space of framed embeddings. So, and the result is again plus 1. We get operad map from BM. Right. Okay, so actually it's wrong. So the statement is wrong. So I just kind of want to warn you. So this is kind of the first guess that one would have, right? Because for the bimodals, if you look for the space of framed embeddings, then this guy becomes on the target becomes equivalent to this framed little disk operad. But it turns out that actually these two spaces are equivalent. So this space and this space are equivalent. So it doesn't help to put the framing here. So actually I remove it. It's not, I mean, it doesn't change anything. The correct answer for the delooping is obtained by taking the homotopy fiber over Sn. So the thing is that we have an action of the orthogonal group on this space. Actually, Sn acts on the automorphism of Bn. And so we need to take the quotient of this. Well, this I think this should follow from the work of Boavida and Weiss. I don't know, have you seen this? But well, it's just appeared in our paper with Julien and with Thomas. Right, just appeared like 2 days ago on arXiv. But I think it follows from, it also can be derived from the work of Pedro and Michael.
I was a little confused when you when you say M bar. You mean you're sort of fixing the action on the tangent bundles, right?
So when I take M bar, I take this homotopy fiber. I take homotopy fiber, right? Embedding model immersions.
But that's equivalent to saying what the differentials do, basically up to a
right.
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 And what's framed? Framed worries more about the normal bundles, right? Or what is that the difference?
Framed embeddings, right? So we have a trivialization of the normal bundle. Yeah.
Exactly. So
we should be standard at the boundary. Standard at the boundary.
Tangent bundle and normal bundle. Okay.
Right. Well, okay, we can discuss it later. I think it will follow from your work. I mean, okay. So
since we're talking about differences, BM is the same that Sander Coopers calls EM?
Right. Yes. Good. So next, all right. So that was kind of about the delooping results, and the nice thing about this space is that it's high connected in the space of embeddings, and we can use the rational homotopy theory to study this object. So when codimension is at least 2, this space is actually simply connected. And we can use the rational homotopy theory to understand the space. And what is going to help us is formality results, so little this operad formality. Okay, so now I will kind of switch a little bit the subject. I'm going to speak about rational homology and homotopy of embedding spaces. I should probably give credit to Pascal Lambrechts. So Pascal Lambrechts was the first who really tried to apply the formality of the little this operad to understand the rational homology of embedding spaces. But I just don't have time to kind of mention his results on the subject. So let me explain kind of directly what's happening for this situation. But first, we have a kind of formality of the little this operad. So theorem, the operad VM is rationally formal. Right. So what it means? It means that there is a zigzag of equivalences of operads between the singular chains and rational homology. And in fact, not only this operad is formal, but also the inclusion. So the map of operads is formal for codimension at least 2. Actually, when codimension is 1, Thomas and I, we prove that inclusion is not formal. So this is really work of several people. So the last result is due to Fresse and Willwacher, who showed that.
What does it mean for a map to be formal?
Right. So it means that there is a zigzag of maps. There is a zigzag of maps of commutative. So instead of having a map, you are going to have like right. So instead of having this guy, you have like singular chains of Bn and you want to construct a similar zigzag which commutes. Right.
Well, maybe one should also emphasize here, formal means you can replace the chain complexes by their homology.
Right, that's right.
Without losing information, basically.
Yeah, this roughly what it means, yeah.
But you're not looking at any co-algebra structure or so here.
So that's exactly what I want to say now.
Okay.
So the thing is that it's not only formal, but it's Hop formal. So that's what I'm going to add. And so Hop means that we actually, instead of looking at the operad and chain complexes, we look at the structure of an operad in coalgebras. And we have this kind of stronger statement. And actually this stronger statement will help us to understand the rational homotopy theory. And so using this Hop operad formality, so we proved
Do you have a zero space in your operad?
sorry?
Do you have a unit like a zero space in your operad?
The base point?
Zero array operations.
Zero array operation?
Yes. Actually, it is important. It is important, yeah. So otherwise, the next statement will not be true. So theorem. So Fresse and Willwacher. So I think it was a couple of years ago. So first of all, we get that the space of operad maps is n minus m minus 1 connected. So which means that it's simply connected when codimension is at least 2. So secondary, so which means it makes sense to speak about its rational homotopy type. However, when codimension is 2, rational homotopy theory doesn't work very well. So in the sense that the maps between the stages of the Goodwillie tower, so when we kind of approximate by the arity, somehow they don't become higher and higher connected. So therefore, we really want codimension 3. So for n minus m at least 3, the rational homotopy type, so the Quillen model of the rational, let me say, the rational homotopy type of this space so is encoded by the L-infinity algebra of homotopy by derivations so of the Hop algebras map, Hop operad maps. And I cannot have the map of just rational homology of BM to the rational homology of BM. So essentially, what this theorem says that like all information about the rational homotopy type of this space is encoded by just map of this map of operads, right? So this operad is associative operad when m is 1, right? And it is Poisson operad with bracket of degree m minus 1. And so the claim is that from this map we can read like all information about the delooping of the space of embeddings. So what it means, so what I mean by the homotopy by derivations. So we need to consider the category of operads in differential graded coalgebras, co-commutative differential graded coalgebras. So we need to take the cofibrant replacement of this operad. So essentially it means that this operad should be cofibrant as operad in chain complexes. And we need to take a fibrant replacement of this operad, so which means it should be, roughly speaking, co-free in every degree as a coalgebra. Right? So it should be fibrant as a commutative differential graded coalgebra in every degree. And we need to consider the space of the by derivations, so derivations which respect both coproduct and operad structure. And that's where the actually graph complexes appear. So when we take the fibrant replacement of the target, we need to use the Kontsevich model, Kontsevich operand of graph complexes for this operand. And so more explicitly, so this L-infinity algebra is actually can be described as a hairy graph complex. So this is another theorem from. So this by derivations of this map. So is equivalent to certain hairy graph complex. Well, actually, I should kind of emphasize that the answer is slightly different when m is 1. So when m is greater than or equal than 2. So and really the difference comes, so the complex will be the same. Essentially the complex is the same up to regrading. So when is, m is 1 or m is exactly 1. So the complexity will be the same, but the L-infinity structure will be slightly perturbed for m is 1 because you see the operand in the source is different. So this makes things more complicated. And actually Thomas used a deformation quantization approach to really make it, to write down explicit formulas for the perturbed L-infinity structure in case m equals to 1. So in case somehow m equals to 1 nodes, they're more complicated in a way. So and so here we get just usual DG-Lie structure. So DG-Lie structure on and here we get some perturbation. But as I said, as a chain complex, it's going to be equivalent. It's just the same complex. On the level of differential, it is the same. It's just bracket and higher brackets are perturbed. So what is a hairy graph complex? It is essentially the commutative graph complex. So it looks like a commutative operand graph complex, but we also have kind of external vertices, which are not labeled. So roughly speaking, you should think about these guys, external vertices. They somehow lie in Rm, and internal vertices, they lie in Rn. So this is kind of different with graph complexes that Thomas considered. So Thomas considers a group of diffeomorphism, and in that case, you don't have external vertices. You have only internal vertices. Right? Even so, in his picture, he had trees that appeared. Right? So he had univalent vertices, but still every vertex had the role of internal vertex. So here we have two types of vertices, and roughly speaking, it tells you the interaction between points on your node and points in the ambient space. Right? That's kind of how we can see this. So the differential is similarly obtained by not contraction of an edge, but rather expansion of a vertex. Right? So they're always connected. Right? So the Lie algebra structure, maybe I should say what exactly is the bracket. So I don't have time to really explain how these graph complexes look like. So the bracket, so if we have two graphs, so with another graph, another hairy graph, so the bracket is going to be just the sum of possible connections of one of the external vertex of the first graph with one of the external vertex of the second, right? And minus plus it goes in other way around. Right, so we just kind of do the same. Right. So this is the bracket, and so in case m is 2, there is no higher brackets. But we get some deformations, L-affinity deformation, when m is 1. And Thomas kind of made it explicit in a different paper. Now I want to speak about some work in progress. So let me just mention it's work in progress with Benoit Fresse and Thomas Willwacher. So we try to understand the rational homotopy type of the space of embeddings with the target Euclidean space. So let M be a compact submanifold of Rm. So possibly with boundary or without boundary, possibly disconnected and possibly having components of different dimension, so it doesn't matter. And we look at the space of embeddings, modular immersions of M in Rn, where codimension is at least 2. So notice that in this case, since M is compact submanifold of Rm, its handle dimension will be strictly smaller than M, right? And therefore, in this case, we see that the codimension is actually at least 3, and therefore good-Billy calculus can be applied. And also, good thing is that we have codimensions at least 2, and therefore we can apply the formality result. Right? Somehow things kind of match well together, and so now the question is how we can understand the rational homotopy type of the components of the space. So what is the rational type of the components? Right, so and right, so I can probably change this one. Right, so right, and as I said, particular example would be to look at the space of embeddings of a collection of Mi inside Rn, right? Assuming that right, so we have right, so we can fix some inclusion of this disk. So we essentially want to have the codimension to be at least 3, right? So that the left-hand side can be embedded inside Rm, right? So we really want to have some kind of. So this will be kind of particular example. And in particular, we are able to see the like rationally the Hafliger's computations of the link groups, and codimension is for the links is at least 3. Right. So to understand the rational homotopy type of the space, we have the following. So we define the certain Hairy graph complex. Right, so N stands for the ambient dimension, and AM is a CDJ model for the manifold M. So we claim that so we get we just need to know the rational model for M. And so we define this Hairy graph complex is a L infinity infinity graph complex algebra. So what I mean by this is just a graph complex with the structure of an infinity algebra. So probably I don't have time to elaborate on the structure, so how exactly the infinity structure looks like. So let me just state what we proved, or certain statements in my theorem are going to be just whole proof. Actually, I need more space. Maybe I just go there. So, theorem in progress. So first of all, we believe that every component of this space, so with this condition, is nilpotent. So for every component, for every component connected component K of this space, is nilpotent. So it's rational nilpotent space. So second, for each component K, one can assign a certain Murray-Cartan element in this algebra. So for every K, there exists a Murray-Cartan element zk, so it lives in the this hairy graph complex. So it lives in the degree -1. So there is a difference between topologies and algebraists. So the algebraists like when they work with co-chain complexes, and the topologists they prefer chain complexes. So that's why Thomas was talking about the Murray-Cartan elements in degree 1, but I prefer -1. So we can assign this Murray-Cartan element, and the rational homotopy type of, so the Quillen model for K can be expressed as a is given by just the hairy graph complex that we want to truncate, and we want to twist it by this Murray-Cartan element. So another thing is that so the associated Murray-Cartan element for the unknot is just trivial. So the for the unknot this element, Murray-Cartan element Zu is just 0. So which means that if you want to understand the rational homotopy type of the unknot of the component of the kind of trivial embeddings, then we just need to take the hairy graph complex and we just truncate it in positive degrees. Right? And the last thing which I believe is true, but we don't have any argument for it. So for this, we kind of it relies on some technical business.
But the unknown M as a sphere.
No, unknot we have by unknot I mean the component of the inclusion, right? So we have the inclusion of the manifold M inside Rm. We started with, and this is inside Rn. Right? It's essentially any component which whose embedding is isotopic to any knot which is isotopic to a knot in 2 dimensions smaller. Right, and this is unknot. And last statement, so this is really my belief based on the just personal experience of working with these spaces, that there are only finitely many components associated to the same Murray-Cartan elements. So there are always finitely many components associated to the same Murray-Cartan element. Well, the same again, I mean up to the gauge transformations, up to gauge transformation. Right, so well, essentially, the thing is that if you look rationally on this space, so we know that rationally it is just an abelian group, and what we can see from this model, so essentially the Murray-Cartan element can be think of as a generalization of the Kontsevich integral in high dimensions. And also I should mention that actually it's always lives in the loopless part, right, by dimensional reasons. It always lives in the loopless part, and somehow it should be something which encodes the Milnor invariance. And that's exactly what Haflinger obtained, when he studied, this abelian group. So this is kind of easy to describe using the Lie algebra and using the Lie operad. And so there, right. So we can see that the Murray-Cartan elements are really going to be. There will be finitely many corresponding to the same thing. But for this, we don't have an argument yet. So just kind of conjecture I have. Okay, so that's it.
Questions?
So for this codimension, for this work in progress, and codimension, like a classical codimension 2,
right?
Could you still obtain some results for the levels of the? So you said that
right. So, well, the thing is that so good thing. So when we look at the map of operads, we have so we know that so we have similar results for the embeddings dm to dn. We can describe it as it's equivalent to the space of maps of operads, but actually truncated operads from Bm to Bn. This will be the case approximation to the tower. And when we take the partial approximation, we know that the rational homotopy type of this case, of this space, is given by the homotopy by derivations of the Hopf truncated operad map. So we can take the homology of Bm, view it as a K truncated operad, and so we can look at the the natural map. So this is true that rational homotopy of this space is encoded by this guy. So rationally we understand the delooping in the classical case when m is 1 and is 3, but we cannot say what happens at the limit because. Well, roughly speaking, because tensor product with rational numbers doesn't commute with the projective limit of abelian groups. So that's why we cannot say what, right, so we can say what is the limit of maps from Bm to rationalization of Bm, but it's not the same as the, when you remove the Q. So rationally it's not the same.
And what about these links? I mean, can you?
So these links, well, in this case, we cannot apply this construction because you see, we need to have a right. So in this case, we have that codimension should be at least 3 because we want to have a manifold which embeds in a submanifold in a linear subspace of codimension 2 less. So therefore, it cannot work to understand embedding from S1 to R3. So the closed embedding doesn't work. Unfortunately.
How about these Morez-Kaplan elements? I mean, what do they depend on? Is that K?
So these are elements, so zk lives in degree -1. So how we define it? I think Thomas has an idea how one can define this element. I hope that it can be obtained as some generalization of the Botaup's integral, because well, it lives in degree -1 and not in degree 0, because we always make a shift in degree by 1, right? When we study the homotopy of a space. So actual geometrical degree is 0 for the space, for this Morez-Kaplan element. So this regarded as some kind of invariant. So this
Are they going to be homotopy invariant?
Say it again.
Are they going to be rational homotopy invariant?
No, I say that it is isotopy invariant. Isotopy invariant of links, yeah. But also, not only kind of it helps to distinguish this high-dimensional embeddings, but also it determines the rational homotopy type of each component. Yeah.
I had the impression I understood gradually in your talk that this HGC mechanism, it is a way to go from the Sullivan model of rational homotopy theory to the Quillen model, right? I mean, you start with a CDGA of some kind?
Well, the thing is that we always try to work with homotopy by derivations of certain algebraic objects. So here we have by derivations of operads, right? In the other example, we need to look at the by derivations of right models, right? So we have a right. So as Thomas explained in his talk, right, we go with combined models of BM. So here we have embeddings of disks inside M, and on the right hand side we have BM. So the next step is replace this space by rationalization, right? And it does not change things much because every component is nilpotent. So what we want to prove, what we hope to prove. But next step is to put this Q inside. And because once this Q is inside, so this is, I mean, this space is easy to describe. It's the same as a space. We can take just the space of right model maps of the hope for cooperads. So we take like singular chains of BM. Right. So well, maybe I should say that. So rather, we really want to take right comodals. So we have the. It's not loops. It is the RAM complex of BM. So it is cooperad. And we take the omega of BM to omega of the space of embeddings disk. So, and it's really so now we need to look at the right model maps of this algebraic object. So this is really maps of right comodules over the cooperad in cochain complexes.
My question is more elementary, I think, more abstract. Look at the lines above what you just wrote. You wrote AM is a CDGA model for M. Does that
right?
As in Sullivan?
No, AM, right? This is Sullivan model of M, and from this we can produce Quillen model. But at the same time, we can also get easily the Quillen model for the components. We just need to, instead of looking at the connected graphs in our complex, we take the complex of all graphs. Right, so we should take just kind of bar construction, like Harrison complex of the infinity algebra. So I mean, it's still kind of the same language, but it's more natural to look at this hairy graph complex. I don't know. Yeah.
More questions? Okay, no more questions. Then coffee, and we continue.